Doing problems 47 through 49, and this is one where we're going to indicate if the bond order of the following compounds is A, 1, B, 1.5, C, 2, D, 2.5, or E, 3. So again, this is another scratch paper one, so you're going to have plenty of practice drawing these by the time you have to actually draw one
For real.
for real. Okay. Wow, that was a neat sound. Okay. Number 47 is nitrogen. And my energy axis. And what's the first combination? What am I going to get?
You got sigma 2s, sigma star 2s. You got 2 or pi 2p, sigma 2p, pi sigma or pi star 2p,
Star 2p.
and sigma star 2p.
Draw lines correlating the molecular orbitals with the atomic orbitals from which they were created, which may be a little bit redundant, but it's going to be required. So, you know, but it does, it just reinforces the fact that these molecular orbitals were created out of the p orbitals, and these were created out of the s's. And nitrogen is what?
Nitrogen 5.
5. So I have 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. And that gives me 10 electrons, which I place in according to Hund's rule. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Which gives me a bond order over 1/2 what?
A minus 2.
Okay. 2, 4, 6, 8. Minus the 2. So I have a net triple bond. And just to round off the day, is it diamagnetic or paramagnetic?
Diamagnetic.
Yeah. There was no unpaired electrons, so it's diamagnetic. Okay. Now, what was the next one? So that was bond order 3. That was option E. Now, for the, if I were to remove an electron from that to make the dinitrogen cation, I'm going to be taking which electron is the most likely one, the most easily removed.
The higher energy.
The sigma 2p. And so I'm just going to draw, here I'm just going to draw the molecular orbitals. Sigma 2s, sigma star 2s, pi 2p, sigma 2p, pi star 2p, and sigma star 2p. So I place those there, and I'm going to put in, now I'm going to put in 9 electrons. And I have a bond order equal to 1/2. What's this time?
1/2 7 minus 2.
So I have a bond order of 5/2, which is 2.5. So I actually have an increase or a decrease in the bond order?
Decrease.
Yeah, it's a what?
Decrease?
A decrease, yeah. It's a decrease in the bond order, so we get longer or shorter?
Shorter.
Longer.
Longer.
Longer, because and the reason for that is because the nature of the electron that was removed. It was what kind of an electron?
High energy.
It was a bonding electron, so if I remove a bonding electron, I'm going to have a decrease in the bond order, and what's going to happen to the bond length?
Increase.
There's going to be a longer bond, and this is the dinitrogen cation. And so that was option 2.5 was option D. And then last in this series is so you can see we pretty much beat this question to death. It was in multiple choice, the true false. This is in the multiple choice, but we've addressed it several times, all of these aspects. So that type of replication will be on the test. So, you know, once you know this, you're going to be able to answer all those questions. There are those who say this test is easier. The test actually should be getting easier as we go. But then, yeah, who pays attention to people who talk like that?
Yeah. Bunch of nerds.
People say a lot of things.
People thought communism was awesome.
49.
What is this? This is, yeah, 49. Yeah. One oxygen atom, 2s. 2s. 2p. Now, what comes next?
Oxygen is group 6.
Yeah, well, wait a minute. What's this called?
Oh, that's sigma 2s.
2s.
Sigma star 2s.
What next?
Pi.
Sigma 2p?
Yeah. Because it's oxygen. It's where the inflection occurs. The sigma 2p and now the pi.
Why is that?
1 second. 2p. Sigma star 2p. It's because as I proceed from nitrogen to oxygen, as I was proceeding across the periodic table, I get smaller and smaller and more electronegative. And so the electrons are held more tightly, and in particular, it's this sigma 2s, this very low-lying molecular orbital, which has less and less electron density in the region between the atoms. It's more localized on the oxygen atoms themselves. And so that means it's not as repulsive. There's not as many repulsive interactions between the sigma 2p Z and the sigma 2s. And so that lower repulsion lowers the energy. It doesn't take as much work to place electrons in there. 'Cause what is energy again?
Work.
The ability to do work. So it doesn't take as much work to place electron density into this sigma 2p molecular orbital because there's not as much electron density already there. And that's because of the increased electronegativity.
It'd be the same for fluorine too, right?
Yeah, it'd be the same for fluorine. It's even more fluorine's the most electronegative of all the elements in the
So it's only oxygen and fluorine that does that?
Yeah, it's only with oxygen and fluorine. For everything up to there, it's just like the ordering is the same you see with nitrogen. But now that we're at oxygen, we're going to see this. Oxygen is what group? So I have 1, 2, 3, 4, 5, 6 on each oxygen atom. And that's going to give me 12 electrons in the molecular orbitals. Place those in following Hund's rule. 7, 8, 9, 10, 11, and 12. So I have, what is this going to be? What kind of molecule is this going to be?
Paramagnetic.
It's going to be paramagnetic because I have 2 unpaired electrons. In fact, a lot of the chemistry and the reactivity of oxygen is understood more easily here. Because in addition to its magnetic behavior, it has 2 unpaired electrons. That is going to give it an enhanced reactivity. It's going to tend to, these electrons are going to tend to pair up with when it bangs into another molecule. It's what you call a radical, an unpaired electron. So oxygen is traditionally extremely reactive, whereas nitrogen is extremely inert. If it wasn't for the 70% or 78% nitrogen in the atmosphere, if we were in a pure oxygen atmosphere, we'd flame on real quick. So it's it's a good thing. Live in the atmosphere that's 80% this and 20% that. So what's the bond order here?
So 1/2 8 minus 4.
Well, I have a paramagnetic material that has a bond order of 2, and that would be option C. So the bond order of 2 agrees with what we had. So Lewis was fine as far as that goes. It does give you a good accurate representation of the bonding pattern. But with Lewis, we didn't have all these other things revealed. Same thing can be said for dinitrogen. We knew it was a triple bond. We predicted a triple bond with the Lewis structure. Turns out it is a triple bond. But in contrast to the nitrogen, which upon ionization has a decrease in bond order because I removed a bonding electron. If I were to remove an electron from oxygen to make the O2 cation, I would see what?
2.5, it would get the bond strength to increase.
The bond, yeah, the bond order would increase. The bond would get shorter and stronger because the nature of the electron that would be removed. The most easily removed electron would be the pi star, the antibonding electron. So I'm removing an antibonding electron, therefore I'm going to have an increase in bond order. And this is indeed borne out by experiment. None of this is revealed by Lewis. So Lewis gave us a wealth of information. We have to be intimately familiar with both models in order to get a real, more complete understanding of the chemistry. Okay, and this is indeed observed. This decrease in bond order, or ionization of nitrogen, and the increase in bond order with ionization of oxygen. Okay? That is a wrap for 47 through 49.